How does math make you feel? Do you enjoy the logic and consistency of algebra? Or do the numbers and letters just seem like a confusing mess? Frequently, I find myself asking, another day has gone by without using y equals mx plus b. And I think that's because too often we're told that we don't need to understand why the numbers work the way they do, just trust that they work and arrive at a solution. See, we're so caught up in solving for x that we forget to ask ourselves the bigger questions. Where does all this math come from? Did we invent the rules of mathematics to solve society's numerous problems? Or did these elegant solutions already exist? In 1886, famous mathematician Leopold Kronecker said, "God made the integers. All else is the work of man." This novel idea tries to address both sides of an age-old question. Is math invented or discovered? And if we really did create all this math, why is it so hard? And if we didn't, how is it such an integral part of the society that we live in? And most importantly, why does it make us feel so dumb? I think the reason that so many of us feel helpless when we try and understand math is because we're using the wrong lens to do it. See, math just has a really bad PR team. They're trying to get people interested, but they're using confusing symbols and variables. I think if we approach math through a different, more visual lens, we may just be able to fix math's PR problem and understand where all this math really comes from. Now, math isn't my forte. It's definitely something I'm interested enough in to talk about on a Friday night, but I'm not a mathematician. For the past 2 years, though, I've been exploring a field called generative art. Broadly, generative art seeks to create artwork through a collaborative effort between man and machine. The artist works in tandem with the computer to code out algorithms that are executed on a virtual canvas. And what separates generative art from more conventional mediums is its ability to get exponentially more precise, detailed, and complex with little extra effort. Just a few lines of code can turn a small canvas into a huge one, and 10 lines into 10,000. A perfect example of this is in one of my favorite pieces, a toy galaxy. The piece looks complex. Thousands of points move at various speeds, each of them eager to make their way to the very center. And while the math behind this piece is just boring old trigonometry, the art itself is anything but. What originally drew me to generative art was pieces like this one. I could be infinitely more creative and precise than I could on paper, making up all sorts of patterns from scratch. As I began creating more and more pieces of generative art, though, I began to realize that my favorite ones were the pieces that almost exclusively used mathematical patterns. Now, in all honesty, that's probably because they required the least amount of work on my end. See, mathematical patterns, while visually stunning and organically beautiful, often come from simple equations that are easy to program and don't require much creativity. Whereas conventional artwork is an expression of the human condition, generative art is an expression of the universal condition. And these patterns can tell us a surprising amount about whether math is invented or discovered. Let's take a look at a pattern that most of you have probably seen hundreds, if not thousands of times, though few of you will probably remember that it's there. Caustic patterns are created when light is reflected off the inside of a circle. Coffee cups have a caustic pattern that's created as light bounces off the edges of the mug. And even though it may be harder to see on some days than others, it's always there. At first glance, it doesn't look like much. Maybe like a crescent moon, maybe even like the logo of the rebels in Star Wars. If we take a closer look and really unpack this pattern, though, it begins to look a bit more complex. Looking at the pattern through this lens, we can make a few really interesting observations. First, all of the lines in the pattern are straight. The pattern itself is curved, yes, but its composition consists entirely of nice, simple, straight lines. What's more interesting is that each of these lines are mapped in a very particular way. It's a bit hard to tell with so many lines on screen. So let's take a look at another recreation of this pattern, this time with only 10 lines. To make it even easier, let's number the endpoints of each of these lines. And as we begin to trace each line, we might notice that they all follow the same pattern. 1 goes to 2, 2 goes to 4, 3 goes to 6. Each line begins at a number and ends at 2 times that number. We can go all the way from 0 to 10, then restart. And as we add more points, we might notice that it begins to look more and more like our coffee cup. Well, this raises a few interesting questions. First, why do coffee cups have this pattern to begin with? Is it just a coincidence? Really good Star Wars branding? Fortunately, the answer is neither. Coffee cups, like most mugs, tend to be pretty small and round on the inside, which means that light can bounce off the edges in all sorts of interesting ways, helping make different patterns. The more important question, though, is what could this possibly tell us about whether math is invented or discovered? The answer to that lies not in the pattern itself, but in its negative space. Though it's a bit hard to tell, the negative space from the light reflections actually creates another pattern, a fractal. Fractals are structures that are composed of smaller, repeating patterns. A really good example of this is Sierpinski's triangle, a pretty basic fractal pattern. We can recreate this pattern in 3 simple steps. Let's start with a triangle. In step 1, we'll divide our triangle into 4 smaller triangles. In step 2, we'll remove our center triangle. And finally, in step 3, we'll repeat steps 1 and 2 infinitely until we get our final Sierpinski's triangle. This infinite self-similarity is what makes fractals both visually stunning and impossible to recreate in the real world. Mankind just doesn't have the tools that are precise enough to make fractals at a significant level of detail. Something as complex as a fractal can actually be modeled using an equation that we all learned in middle school, the midpoint formula. Check it out. We'll start, once again, with a triangle. This time, we'll plot a random point inside our triangle. Then, we'll choose any of the triangle's vertices. And finally, we can find the midpoint between our point and the randomly chosen vertex and plot it. Then we can repeat this process. We'll pick another vertex, find that midpoint, and plot that. Turns out, if we keep going like this over and over, we actually get our final Sierpinski's triangle. Let's speed it up. This animation was made using Jade. Jade is a graphics package that I've been developing from scratch to help me and others make all sorts of generative art. And though we can't physically recreate fractals like these, we can visualize them simply by plotting midpoints and counting to the number 3. Well, you could argue that all we've looked at here are simple patterns that aren't representative of the chaotic world that we live in. But it turns out that just like we can model things like caustic patterns inside a coffee cup and fractals, we can also model things that are more chaotic. For example, can we model something like how wind speeds change in a tornado that sweeps through Oklahoma, or how a wildfire spreads through a forest in California? It turns out that even with patterns that have some element of randomness, math is really good at describing and recreating such phenomena. One such pattern in nature is bird flocking. While flocking, birds make all sorts of intricate patterns while focusing on staying with their flock. Unlike the other patterns we've investigated so far, the patterns made through bird flocking are far from rigid. They tend to have elements of randomness that make the patterns even more complex and difficult to understand. Yet, this may be one of the easiest patterns to recreate through math, because it requires very little arithmetic. Originally devised by a computer scientist named Craig Reynolds in 1986, boids are an artificial flock of birds that mimic bird flocking in nature. Reynolds used just 3 rules to teach his boids how to flock: separation, alignment, and cohesion. Separation forces each of the boids to stay a certain distance apart from one another. This ensures that they don't accidentally bump into each other and hurt themselves. Alignment encourages all of the boids to move in the same direction. Each boid wants to stay with the flock. Finally, cohesion encourages all of the boids to move to the center of the flock, where wind speeds are low and protection is high. Boids are especially interesting to study because they're the first pattern we've investigated so far that doesn't just exist in static things like a coffee cup. They exist in living, breathing animals. And while the process of recreating boids doesn't involve as much arithmetic, the rules that govern them are inherently mathematical. They each have an importance or weight assigned to them, and they create consistent algorithmic patterns. And these patterns aren't exclusive to bird flocking. Think about how we navigate Atlanta rush hour traffic on I-85. So closely packed together, yet maintaining some level of separation as we all move towards our destination. Though the application here is different, the patterns are the exact same. This all begs the question, if we can so accurately recreate such complex phenomena using such simple methods, could math be discovered rather than invented? Through my own experience, I've come to the conclusion that yes, math must be discovered rather than invented. The patterns that I've found most interesting and recreated have ranged from simple to complex to completely chaotic. Regardless of which pattern I was looking at, though, each had a mathematical backing that was so comparatively elegant that these patterns must be based on math, not vice versa. After all, if I can recreate everything from caustic patterns to fractals to bird flocking using just a few lines of code, it makes sense to me that the universe follows math instead of having math conform to the universe. But there's no guarantee I'm right. Just as you don't need to be a mathematician to try and answer whether math is invented or discovered, you also don't have to be a computer scientist or a generative artist. Generative art is a lens that I use to recreate patterns in a way that helps me make sense of them. It's a hobby I love that just so happens to have a secret mathematical dimension. But chances are, all of these patterns are hidden in your favorite pastimes too. If you love going on walks, you'll probably notice the same Fibonacci spiral in a pine cone during fall as you will on the inside of a sunflower during spring. If you'd rather stay inside and cook, you'll notice that your Romanesco broccoli is nothing more than an edible fractal. If you're jogging through the streets of Boston, the fractals you'll see are probably going to be in the form of snowflakes. If you're hiking through the Olympic National Park in Washington, though, you'll see fractals in the branches of the redwoods. And if you're here at the University of Georgia, walking through the trial gardens on your way to class, you'll notice that each of the petals on the dahlia flowers is a fractal too. Let's say you're into beekeeping. You might look at the beehive you're maintaining and notice that the honeycomb is nothing more than a Verneuil pattern, where each line is equidistant from its nearest 2 points. If you don't like being close to bees, though, you'll notice the exact same pattern across the back of a giraffe when you're at the zoo. And if you want to stay away from animals altogether, you'll notice the Verneuil pattern again in the cracked mud of New Mexico. Chances are that no matter who you are and what you love to do, you're surrounded by all sorts of interesting mathematical patterns. Some of these patterns may serve a practical purpose, like the colors that flowers use to attract pollinators. Other patterns might just look pretty. The more you look, the more you'll realize that you're surrounded by simple mathematical patterns that make up our everyday lives. But each of these patterns warrants more than just a glance, as each is an argument in a centuries-old debate about whether math is invented or discovered. Thank you.